about Invoke-Explosion. Combining the day jobs can lead to some explosive results. So, who am I? My name is Leo Darcy. I'm a senior consultant at a small consultancy firm called Power on Platforms. But what you guys may not also know is that I'm a part-time pyrotechnician. So what I do is kind of around the November fireworks season is I'll take a kind of a week or two off from the day job. I'll get kitted up in not a suit and tie and kind of go around setting up professional fireworks displays with a professional company. So, disclaimer, don't try this stuff at home. I'm a trained professional, but as you can see here, they are dangerous. Before we fired the firework, that was whole. They can kill you, maim you. In general, it's not a good idea to play with fireworks. So, just for context, professional fireworks are in some ways slightly different from the kind of fireworks you'll buy from your local superstore. You can see them here. As you can see, they are not as kind of beautifully packed as the consumer grade ones. But in a lot of cases, they're made up pretty much the same way, but there's a big difference. And that is the fact that you'll see what looks like a couple of wires coming out of them, and that's an electrical igniter. That means that basically inside there's a dodgy resistor that when you put enough current through it, it pops. That ignites the black powder. The firework goes off. And what that means is that as a professional company or in a professional display, you can get millisecond accuracy fireworks. You're not kind of lighting this thing and you might wait a few seconds and then it might go kind of thing. So we've got a couple of fireworks here that I actually let off for this display or for the demonstration that you'll see later. Obviously, couldn't do a demonstration here. I'm pretty sure that we wouldn't be invited back. Not to mention, I'm pretty sure TfL would have been rather upset if I'd taken them on the tube. So what are we talking about here? So this is a system called Fire1. This is an electronic firing system for fireworks. It's used by some of the largest companies in the world, and it does things such as the London New Year's Eve fireworks. We also use this system, albeit we don't do quite that large a display. So it's developed by Pyrotechnics Management Incorporated under their Fire1 brand. And what you're seeing here is basically the brains. This is effectively a fancy and very expensive computer. So the way that it works is that you connect your Fire1 control system up. In this case, this is a model known as an XL2. And you connect it to a series of these modules that then take the input from the actual firework leads. So you've got the two connectors coming out the firework, you plug them into the red and the black, and that has a module number and it has a queue number. So the way that the computer works is it has a series of instructions that we program into it that says at 1.5 seconds fire Q1, module 1. And you can do that across all of the modules. It's effectively like a network, except highly resilient. So in terms of module output, these things pump out nearly 20 volts and nearly 5 amps. Because each one of these inputs can actually take more than one firework at a time. So if you want a whole bunch of them to go off simultaneously, you can put in, reading the documentation, if I remember correctly, it's rated to do something like 40 fireworks simultaneously. They recommend 20 to actually give some leeway. And what we've got here is the professional software that they have written and is what you're supposed to be using for programming and controlling these devices. What you can do is actually just preload the program onto the red box, and then in the field, all you have to do is hit the go button. But if you want a bit more control or a bit more testing, then you've got this software called Ultrafire. Now, this is very expensive software, but it is the professional stuff. So what you might have noticed, if you're looking carefully, is there's quite an interesting little data input port that looks an awful lot like a serial connector. And it turns out it is. And I thought, well, there's no automation platform for this, but let's do something dumb and try and work out the serial protocol so that I can hook this up to PowerShell, which has .NET and under the hood, which means that you can talk to serial. So the tools I used to do this was my laptop, multimeter to get things like the voltages and the current. I used a piece of hardware called a Yoctopus. This was a new thing on me, but basically what it allowed me to do, it was man in the middle, the serial port. So as I was pushing commands through the professional Ultrafire software, I could actually look at this was detecting those signals, detecting the responses back, and therefore I could look at actually what was being sent through. And that allowed me to reverse engineer the actual protocol in use. In reality, it's not a massively complicated protocol, but it certainly has some intricacies to it, and I'll go into some of those in a moment. Also, had to use an oscilloscope for a little bit, because as I found out, serial connections, while they're kind of standardized, it's one of these, there's 20 standards, so let's create a 21st standard. And I was having issues where I could detect the command going to the module, and that was absolutely identical to the actual Ultrafire command, but I wasn't getting any response back, and that was due to the control, some of the control lines. So you have to set some of them like basically the control line high, whereas others like the control low. So you have to configure all of these things as part of your serial cable setup. So in terms of software that I used, had to use the original professional Ultrafire software. I located a demo for it. I used YoctoSnoop, which is provided as part of the Octopus hardware, which allows me to view those commands as they were going in and out of the box. And then in the end, I used serial port monitor with the oscilloscope to actually identify things like the control ports being configured and used. So I wanted to create a PowerShell module, and I thought, let's try and use let's try and experiment, shall we say, with some of the best practices. How can I start writing good modules, as this is effectively a from scratch, from new project? And I came up with, or I discovered the build module. And this is a really lovely module in the fact that it gives you the advantages of writing your functions in individual files, making it easily discoverable, but then it will compile it down into a single file so that it is quick to load, easy to sign, and easy to distribute. So you're not distributing hundreds of files. This is available on PowerShell Gallery. I believe that certain people who come to this group may even have contributed to it. But yeah, very interesting module. If you are looking to build your own modules, I would highly recommend looking into build module for its use. I then used a PES framework to act as a logging and system state configuration provider. So with serial connections in general, they are given a COM port, and that COM port can be different between different devices. and also you've got the different serial speeds. So most things run at, I think it's 8200 and 19,200. But so I wanted those to be configurable easily at use time as opposed to being hard coded into the module, or every time you want to use the module having to put those into each command that you send. Then I used GitHub for my source control, and I'm afraid that it is a private repository, and I'm afraid that I'm not going to be able to distribute this due to the fact that I've effectively reverse engineered a proprietary protocol, and the fact that it is to a kinetic system that people could theoretically do damage with if they got hold of the hardware. So one of the key challenges that I found was the protocol itself is made up of a number of bytes and a checksum. And this checksum was not publicly disclosed, as the developers of said hardware were never planning on people doing what I've done. And there's actually no standard for serial connection checksums. It's a case of there's about 15 different ways of doing it. Everyone picks their own one depending on what they feel like that day. It took me several days of actually working this out. I even had some very interesting kind of drawings as I was trying to work it out. I worked it out perfectly for one module with a really idiosyncratic algorithm that included a lot of bit flipping. And then I went to another module and that completely broke it. And the reason for that is that, in fact, it was just a binary exclusive OR. So that is actually how you generate the checksum. Surprisingly easy once you've thought about it. This is actually one of the more common checksums. But if you're thinking about doing a lot of it with more general serial connections, yeah, it's one of those things that it's basically it'll be a lot of trial and error to work through.
Trial and error as like sending it, seeing that you don't get a response, or you manage to like reverse engineer the actual software.
So because I was using a man in the middle, I could see the commands being sent, and I could see what the professional software was sending, and I could see what I was sending, and therefore you could identify, is the packet that I'm sending identical to the one that the professional stuff sent, or the proper one sending, and if it's not, then the chances are there's a problem in what I'm sending. And therefore it's a case of working out, in general you'll have a checksum, and so it's a case of, out of the 7 bytes that you're sending, how do I make the 8th byte equal all of that stuff? And so it's a case of going through some of these algorithms until you find one that matches up correctly. And then obviously proof in the pudding is when you get the when you get the correct response back. So in terms of the final output, and you can't see that because it's on the other screen. There we go. So what we've got is, do I have a mouse? Helps if I turn the mouse on. There we go. So what we've got on the right-hand side, we've got the private module, the private functions. So these are functions that are never designed to be used directly by an end user. So these are things like generating the checksum. So they're nice generic functions, but not necessarily, or shouldn't be directly used. We've got confirm checksum. So that is where the module is sending data back to me. I want to also check that there's nothing lost in translation from the module. We've got get comport, which just returns back a list of available comports from the computer, and test fire ready. And that's something that we'll I'll talk about it now. So in terms of the physical device, you've got what's known as test mode and fire mode. So once you've finished plugging, when you're on site as a pyrotechnician, you're plugging all of these fireworks in. They'll all be nicely labelled, and you'll be plugging them all into the modules. You connect all the modules up, and obviously you can't just fire them all because they're used once. So but you can't you want the display to be as good as possible when the time comes to actually fire it. So these resistors, because they are specially designed, or these igniters are specially designed, they're designed so that you can put a low level of current through them to check that there is continuity, to check that there is a circuit there without actually making them explode. Now that has a level of risk, which is why when we do a test, we make sure that the whole site is cleared. Although normally that's down to user error, when we do a firepower test and someone hits the wrong button, that makes people jump. But the key thing here is that there's a test mode, and then there is a physical key that you have to switch to put it into firepower mode. And you can't fire in test mode, and you can't test in fire mode for obvious safety reasons. So and that's actually hard-coded into the physical box, but what we've got here is a test fire ready, and that just queries the box and says, are you in firepower mode or not? So that we can actually be intelligent at the module level and just say, we're not even going to send those commands. We're going to give useful error messages and say, you're a muppet, don't do that. So where's it gone? Here we are. So we've got, in terms of the public ones, we've got connect panel. So this is creating that initial connection to the module, or so to the firing unit. And that actually creates a permanent serial open connection. You can actually do it without having a fully open connection, but then the module doesn't recognize that it is actually being controlled by a computer, because the proper ultrafire software creates that connection and it effectively uses that as a lock on that device, so that you can't then go and someone else can't just go and connect into it. And you can't. That also disables a bunch of the buttons on the physical unit, so that you're not overriding the computer. You've got disconnect panel, does the opposite. Get module, and what this does is it will get the status of one of those firing modules out on site, and that will either, if you give it a queue number, it will tell you the exact status of a specific queue. If you don't, then it will just return back the full list of everything on that module. You've got Invoke-Explosion, which is the firing command. Sending raw data is if you wish to hard code sending things to it. That should potentially arguably be a private function. You've got test firepower and test module, and what those do, well, the test firepower obviously checks whether there is firepower to that module or not. And what test module does is it says, on this queue, is there an actual circuit there or not? And it will return either true or false to that. So what I did was I wrote a little script. Once I built this, I wanted to kind of start firing it. So I created an Excel spreadsheet. And that is there. So this is and I've got a demo coming up in a minute where I'll show you actually firing from this module. And this is a representative spreadsheet of what I'm actually firing against. So we've got a friendly name description of what the firework actually is. We've got the module number that the actual firework is going to be plugged into, the queue number that it's actually going to be tied into, and then the time I actually want it to fire off. So it's a nice short display. At 1 second, we fire the first one. At 5 seconds, we fire both of the mines. And then at 15 seconds, we fire the slow fountain. So in terms of actually how we do that, we've got a nice script here, which takes a few parameters, which we'll go into in a second. This script, by the way, was knocked up in about 10 minutes, as I had people kind of waiting on me, so it's not the world's greatest script. But a basic don't allow to test and fire if you don't have either one selected, throw an error. We then use the import Excel module. That is one of my favorite modules of all time. It allows you to not need to bother with COM and to actually directly import Excel spreadsheets into a PowerShell object. Very useful. So what we do is we load the Excel spreadsheet in, and that just comes through as an array of PowerShell objects. I then loop through that, and what I do is that I take that, that time information, so the hour, minute, second, and the easiest way I found to create the firing loop was to convert that to total seconds. So all I do is I do a simple hours times 60, minutes times 60 times the hours, plus the seconds. That gives me total seconds, and I just add that to the overall PowerShell object in question. I then also make sure that the queue is not an invalid entry. Reality is I should also be doing that for the module number as well, but time and effort and stuff. So the final thing I do is I sort it so that the total seconds, so that we've got the first ones at the top, the last ones at the bottom, and that means that I can loop through these safely in the actual firing loop. So the next bit that happens is I go through and I do a test. So we go through and we run a test on each of the queues to make sure that what's physically attached to the system is what I'm expecting to fire, vice versa. And then we throw an error if it's not, unless we use the override command. If we are then saying, okay, let's fire this, I then make sure that the system is in firepower mode. So if you're doing a test followed directly by a fire, it basically pauses here and says, please actually physically turn your switch, and then that continues. So in firepower mode, or once we get into the firing system, we are using the stopwatch system from .NET, and we start it. And then it's relatively simple. Because the fireworks are now in order, we can just do a basic loop through. And we say, if current time is less than the firework loop, if the firework is now less than the current time, then that firework should have gone by now, and so we fire it. And all we do is we loop through all of those fireworks and we say, display complete. So what does that actually look like in practice? Well, that is the back of my garden. And here you can see, so these white boxes are the modules themselves. So on the desk, you can see here, we've got laptop talking to firing system. The firing system, you can see, is daisy chained off with these cables to these modules. Those modules are connected to the actual boards. And then those boards have these little stringy igniters out to the individual fireworks. So we've got 2 fireworks in the middle, and then the 2 mines at either side. And so we've got a video. So on the left-hand side, it's not the best view, I'm afraid, but it is what's happening on the laptop, what the PowerShell's doing. And then on the right-hand side, we've got an actual view of the fireworks, and I've synced them up to be pretty much at the same time. So if we give that a go. So just disconnected, just connected. We're going to run in test mode again. Test successful. And ignition on. Everyone ready? Yeah. No, we'll. So you can actually see here that the script itself has stopped because it has fired that last firework, but obviously the fireworks continue at their own pace. So a callback on the phone. So there we are. That is professional grade fireworks being fired via PowerShell. So yeah, I'm not sure I'll be making too many friends with my neighbours. So I was kind of, just to kind of round off a bit, what I've done, you guys probably shouldn't do yourselves. But that's not to mean what the concepts that I've kind of talked about here aren't applicable to yourselves. So there is many different devices out there with serial connections in them. Some of them are more useful to automate than others. But in terms of the experience, and that reverse engineering of those serial protocols, the thing about serial protocols is that they are almost never encrypted, which means that when you've got things like a module number, that'll actually show up in your protocol. So when you've got module 1, module 2, you'll see an ISO 1 and an ISO 2. And you start using that to break down those protocols and say, okay, so that kind of arbitrary number there, that's probably a control number, saying what command you're sending it. You've got your module number there, and then you've got kind of other data there kind of thing. So the other thing you've got to stop doing is stop thinking in decimal, which can be quite challenging at times, but you are dealing with binary, and that means that 4 could, for example, be 4 bits high, which would actually equal 16 or 15. So it's about stop thinking in decimal, start thinking in either hexadecimal or binary, and start looking for patterns. And the other thing that I was kind of having to come across with this is because it is potentially a safety critical system, you've got to think very carefully about data consistency. So what happens is if you can say, okay, I know what that byte is, I know what that byte is, I don't really know what that byte is. What happens if that changes? And you've got to be careful both that that you don't send these control appliances either into some kind of boot loop or just a brick. You've also got to check that it's not going to do something dangerous. So again, be very careful about fail states. So for example, if I don't get the correct, say I send a command, it sends me a response back, but the checksum is not correct. Do I return true? Do I return false? Do I say, yes, it's actually in firepower mode, or no, it's not? Things like that. You've got to be very careful about not giving erroneous data to the user, and you've got to be even more careful to not give safety critical erroneous data to the user. If you're only testing against a single device, single model, as I was only able to get hold of an XL2. I'm assuming that some of those things relate to things like model number. What happens if I go and get an XL4, which is the bigger brother? What happens if that changes? So if you are, for example, automating, I don't know, an air conditioning unit, for example, what happens if you plug it in and there's actually 2 different modules? You've got to be very careful about your testing, because a lot of these things will share code or share control mechanisms, but because they were never designed for it, you have no idea what those original developers have just changed and not told anyone. So yeah, what happens when the checksum fails, for example? And what happens if the device sends back old data? And because these serial connections are designed for lossy networks in a lot of cases, they will tend to repeat their data if they don't believe that it has been sent properly. So handling those kinds of states can be quite interesting, and you need to be careful about these things. But overall, the project was a bad idea. don't do it. But thank you very much. Any questions?
Any questions?
So, well, the next thing I'm doing is a talk at PowerShell Day UK. So you should all come along and see my talk then.
I asked if you have the piece of code that actually construct the packet.
Yeah, so the way that the module works is that we've got let's say we go to the connect panel. So what I do is I generate the array just using decimal connections. And that's again where the thinking in decimal versus thinking in hex has bitten me on the arse more than once, as I've gone and put in 13 and then wondered why it came out as 0C, for example, or something. And then what I do is I send that to the raw data or sending raw data function. And what that does is it takes a byte array of the actual data, kind of timeout functions. There are certain commands that I found that just ignored the checksum. They just zeroed it for whatever reason. So I've got to be able to handle, do I respect the checksum or do I not respect the checksum? And then a switch to tell the command to expect no response back, so it's not sat there waiting. So what we then do is I grab the port information that I've already saved using the PowerShell framework. And then I set up things like the control ports, buffer sizes, things like that. And that's all what I pulled from the PowerShell from the serial port monitoring software. If the timeout's dodgy, I just set it to 5 seconds. What we do is I generate the checksum off of the data that I've pulled into the function, and then what we do is we tell it to send the count. We're creating a new. We create the result as the same size as the data that we send, because it mirrors it in this software. So if I send a 12-byte packet, it will respond with a 12-byte response. So then what we do is we just send the data with the right command, and then we wait for the response. And this response, because of the way that it works, it can all happen instantly. It can be asynchronous, which is why I've got a very complicated looking loop that basically looks how many bytes are available to be read. It reads that out of the buffer. If it's less than the total amount of or the total expected size of the response, I kind of loop for that timeout. If not, I just continue through. I then check I then check that the checksum is accurate, and then I return the response. And if the checksum is inaccurate, I don't directly modify the response. I believe what I do is write a warning. So I write a warning out to the user that the checksum was invalid, and therefore they should be careful, but I don't necessarily zero the actual data being returned. Any other questions? Okay then.
Thank you.
Thank you very much.